So, good morning Year 11 and welcome to the third video looking at skills from GCSE that you need to be familiar with so they can be built upon for the more complicated AS concepts. And today we're going to look at titrations because these do come up a lot at GCSE. Basically every year there's going to be a question on titration, and pretty much the same is true at A-level. Of course, as you might expect, the questions at A-level are slightly more involved, but they really do build on the basics of what you would expect from GCSE. So hopefully this sort of information is looking familiar to you. Words like pipette here and burette at GCSE, you did need to know the difference. There were questions asking when you'd use one over the other, but you really do need to know those terms by now. Also, the number of indicators that you know goes up slightly, and certainly by year 13 you need to know the points at which they change colour. But we'll come back to that in a second. So here's a question that I hope you can all do. What mass of iron 2 hydroxide is made when 30 centimetres cubed of 0.2 mole per dm cubed sodium hydroxide is added to excess iron 3 chloride solution? I'll give you the equation there. So iron chloride aqueous plus 3 lots of sodium hydroxide forms iron hydroxide solid, a precipitate, and hopefully you know the colour of that from GCSE, and 3 lots of sodium chloride. Have a think, pause the video, and then I'll give you the answer. Okay, well we're going to start with the amount of sodium hydroxide solution. So we have a solution, 0.03 decimeters cubed. Remember always to convert centimeters cubed into decimeters cubed when doing concentration calculations. Multiply those together to get the number of moles of your sodium hydroxide. Well, we know that 3 moles of sodium hydroxide makes 1 mole of iron hydroxide. So therefore we know from the ratio that we're going to make 0.002 moles of iron hydroxide. From that point on, it's very straightforward. We use our standard moles equals mass times mr, mass equals moles times mr calculation to get that the mass is moles times mr, so 0.214 grams of iron hydroxide. Hopefully you're able to do that. And here's another example. What is the final concentration of lithium chloride when 1,200 centimeters cubed of chlorine are bubbled through a 500 centimeter cubed excess of lithium bromide? So this might be slightly more complicated, but we're given a volume of a gas. So let's start with that. The only thing we can initially find the number of moles of is that we've got 1.2 decimeters cubed of chlorine. The number of moles, 1.2 divided by 24, 0.05 moles of chlorine gas. Looking at the ratio from the equation, it's a 1:2 ratio, so we're going to make 0.1 moles of lithium chloride. Okay, so what is the concentration? Well, don't get confused, this is the amount of gas here that we bubbled through, but it's not the final volume of the solution. The final volume of the solution is 500 centimeters cubed or 0.5 decimeters cubed. So concentration is moles over volume. 0.1 moles of lithium chloride divided by 0.5 decimeters cubed gives us 0.2 moles per decimeter cubed. Now, all of this is stuff that you knew at GCSE. Putting it together in this sort of way might have been new to you. You wouldn't really have got a question like this at GCSE where you're asked to go from a gas volume to a solution concentration or a mass to a solution concentration, but there's no reason you couldn't. And by this point, you should know how to convert any mass, solution or gas into a number of moles. Moles to moles using the equation. This is always the second step in any mole calculation. Use the equation moles to moles and then use these 3 equations at the end. I said before it would be a good idea if you got beyond using these triangles, because for some of the more complicated equations you're going to have to use, they start to fall down. Now, particularly important application of mole calculations, as you know, is going from the concentration and volume of one solution to find the concentration or volume of another solution, and this is what we're doing with a titration. So here's an example. You should be able to do this from GCSE, so I strongly suggest you pause the video and check you can. 25 centimetres cubed of a 0.2 mole per decimetre cubed sulfuric acid was neutralised by 37.5 centimetres cubed of potassium hydroxide. What is the hydroxide concentration? Pause the video, work it through. Right, at A level you would certainly be expected to be able to generate this equation. Sulfuric acid H2SO4, hydrogen sulfate if you get stuck. And of course you know already from my previous video that sulfate is SO4 2-, so therefore you would need 2 H pluses. Okay? 2 lots of potassium hydroxide, potassium sulfate, and water. This is what I'm saying. If you don't know your formula, if you can't work them out, you are going to be in trouble because you won't even be able to generate the equation for a question like this. Solution. We've got 25 centimetres cubed of 0.2 mole per dm cubed. Don't forget to put it into decimetres cubed. And so we've got 0.005 moles of sulfuric acid. The ratio is 1 to 2, so that means that we need double that number, of potassium hydroxide, 0.01 moles of potassium hydroxide. We know the final volume, again don't forget to put it in decimeters cubed. Concentration is moles over volume, so 0.27 moles per decimeter cubed. You should all be able to do this. At GCSE, I might have encouraged you to do an equation like this using tables. Now, hopefully what I said to you was only learn the table method if you don't plan to do it. And I really do not recommend that you use tables at A level, because quite often the mark scheme is asking you for specifically labelling the number of moles of this or the number of moles of that, or substituting into equations correctly. And in particular, as you'll see towards the end of this video, it's not always the case that we're going to work from the concentration and volume of one thing all the way through to the concentration and volume of something else. Here's another example for you to try. What volume of 0.4 mole per decimeter cubed sodium hydroxide is needed to neutralise 50 centimeters cubed of 0.1 mole phosphoric acid? Have a think, see if you can do this without using tables. Here's the equation. So phosphoric acid, again, hopefully you know phosphate, PO4 3-, hydrogen phosphate, therefore 3 hydrogens needed to neutralise that charge, hence H3PO4. Sodium hydroxide, you should know, 3 of those. Sodium phosphate and water. So we know the concentration and volume of hydrogen phosphate, phosphoric acid. So the number of moles of phosphoric acid, 0.005. As we can see here, the ratio is 1 to 3. So we need 0.015 moles of potassium hydroxide. We know the concentration in this case. We're trying to find the volume. So volume is moles over the concentration. So 0.0375 decimeters cubed, which we might convert into 37.5 centimeters cubed. I hope you are able to do these 3 steps for titrations. As I've said up there, and it's kind of hidden by my head, don't confuse gas volumes and solution volumes. You must make sure that if you are talking about the gas volume, then moles is volume over 24. And if you're talking about solution volume, moles is concentration times volume. Don't confuse those two. Lots of students do. You do need to remember the basics of setting up a titration, so remembering how to use a pipette filler. Filling that pipette exactly up to the line, so that you've got the line here and that your meniscus, because remember the water, the liquid isn't flat, the bottom of the meniscus is on that line as you look directly from it. It's often called a parallax error if you're looking from above and below and you think it's on the line and it's not. You need to be looking directly towards it. So you would use a volumetric pipette to transfer exact amount of one solution. In this case, we're transferring 25 centimeters cubed of alkali. It doesn't have to be the alkali, it doesn't have to be 25 centimeters cubed, but it is an exact volume. You know it very accurately, very precisely. You're going to then put that into a conical flask down here, and you're going to add a few drops of an indicator. The ones you need to know: phenolphthalein, methyl orange, and litmus, and you need to know that the colours that they go in each solution. You will then set up a burette with your, in this case, acid. Make sure the tap is closed, quite important. You ideally don't want to fill the burette when the conical flask is underneath, just in case. Don't pour into the burette from above your head. Remove the funnel. Record the starting volume of acid. And this is reminding you that you need to read all volumes to the bottom of the meniscus from eye level. You would perform a rough titration, swirling the flask while you let the thing run in. As soon as the indicator changes colour, you close the tap. You continue to swirl to check that the colour persists. Sometimes the colour will go back because the reaction takes a short while to complete, and then it may be that you haven't quite reached the end point. But once that colour persists, you will record the final volume on the burette, and the difference between those is your rough titer. Remembering the precision here, so in this case here, looking at this burette, we can see 30, 31, 32, 33, 34, 35, 36, 37, so that is 36.50, and that's at the, let's say, the end point. But let's say that it started somewhere else, like let's say that the start was 01.00, okay? So notice that we would record this number of decimal places where this is a 0 or a 5, and when we take the difference, that would be 35.50, okay? So the titer would be that. Be careful when you're recording the number of decimal places. You will lose marks at A level for not recording to the right number of decimal places. Wash out the flask, refill with fresh alkali solution, refill the burette if needed. Basically, you add most of your original rough titer, and then you finally add it drop-wise. If it starts to change colour, close the tap, continue to swirl. And you will normally be told what concordant titers are. But as a rough rule of thumb at GCSE, they were 0.2 centimeters cubed. At A level, its titers within 0.1 centimeters cubed. Okay. So here's an example, concordant results. You might be asked to complete the table, find the concordant results. Well, the titer here, 26.00, do record it to the right precision. 24.00, this would be 25.10. this would be 24.10, and this would be 24.05. As we look at this, our rough titer is an overshoot, quite clearly, not a problem. This one is too large. Our concordant titers, all of which are within 0.1 of each other, are titers 2, 4 and 5. If we're working out the average titer, we wouldn't need to be told that it's a concordant titer. We would just add up. If we're told to work out the average titer, we won't always be told to only average the concordant titers, but we should know to do that. There's some discussion about when you're giving the average, whether or not this should be given to the same precision as the starting data, so be led by that. So maybe it would be better to record that as 24.05, because otherwise you are inventing precision. But let's have a look at how that can be extrapolated to an A-level question. A student added 627 milligrams of hydrated sodium carbonate to 200 centimeters cubed of 0.250 mole hydrochloric acid in a beaker and stirred the mixture. After the reaction was complete, the resulting solution was transferred to a volumetric flask made up to 250 centimeters cubed with deionized water and mixed thoroughly. Several 25 centimeter cube portions of the resulting solution were titrated with 0.15 mole per dm cubed aqueous sodium hydroxide. The mean titer was 26.6 centimeters cubed of aqueous sodium hydroxide. Calculate the value of X in sodium carbonate .xH2O. Show your working, give your answer as an integer, 7 marks. Okay, let's have a look at this. Okay, the way to tackle a question like this is to draw it out. And we start off with a beaker. And that beaker contains 200 centimeters cubed, 0.2 decimeters cubed, of 0.250 molar HCl. And into that, we've put 627 milligrams of hydrated sodium carbonate, Na2CO3.xH2O. Now, once that reaction is complete, we've taken that solution and we've put it into a big volumetric flask. And then we've made it up to 250 centimeters cubed with water. We've mixed it thoroughly. We've then taken a 25 centimeter cubed portion of that final solution and we've done a titration. We've put that into a conical flask. And we have done a titration into that conical flask. So there's my tap. And what we used here was 0.150 molar sodium hydroxide. And we're told that the mean titer was 26.60 centimeters cubed of that. Okay, now start with what you know. We know about titrations. We're going to start there. Okay, first thing is we can work out the number of moles of sodium hydroxide. So moles is concentration times volume, remembering to put the volume into decimeters cubed, so 0.150 times by 0.0266 is, if I can find my pointer, 0.00399 moles of that. Okay, Now, we know what we're doing here is we've got the sodium hydroxide in this, and this is leftover hydrochloric acid. And we know sodium hydroxide to hydrochloric acid is a 1-to-1 ratio. So NaOH plus HCl going to NaCl plus H2O is a 1-to-1 ratio. For a question like this, you'll only be asked about common acids and alkalis, so that you don't have to waste time generating the equation. So that means the number of moles of hydrochloric acid down here must also be 0.00399. Right. At this point, you could have gone and done what you did at GCSE and worked out the concentration of that hydrochloric acid, but that's not what we're going to do here. And this is why actually the table method starts to fall down. What we know is that this 25 centimeters cubed sample of from the volumetric flask contain 0.00399 moles. So the question we've got to ask ourselves is how many moles were there in that whole volumetric flask? And the answer is 10 times. Look at that. We've taken 25 centimeters cubed from a total of 250. So in the whole flask, there must have been 0.0399 moles of HCl. And if you needed a calculator to do that, you are in trouble. Right, what can we do now? Aha, all right. Looking over here, we know that we started off with 0.2 decimeters cubed of 0.250 molar hydrochloric acid. So the moles of HCl we started with, so moles of HCl at start, is concentration 0.250 times volume 0.2, which equals 0.05 moles. Right, so we started with 0.05 moles. By the time we get to this volumetric flask here, we've got 0.0399 moles left. So moles of HCl used in reaction with the carbonate Na2CO3.XH2O, this is this first reaction that went on in the beaker, is the amount we've got at the start, 0.05, that's what we put into the beaker, minus the amount that was left over by the time we got to the volumetric flask, 0.0399, which equals 0.0101. All right, so that's the number of moles of hydrochloric acid used in that reaction. So we're getting very, very close. How can we work out the moles of carbonate? Well, again, we need our second reaction. We need to know that in this reaction that occurred in the beaker, hydrochloric acid plus Na2CO3 formed sodium chloride. There must be two of those. So therefore there must be 2 HCl, and you can complete the equation if you want, CO2 plus H2O. But the key thing here is that 2 of those reacted with 1 lot of sodium carbonate. So therefore the moles of Na2CO3 equals half of this number, 0.00505. Alright, so number of moles of sodium carbonate. So from this point we've got a few options, but what we can do is we can work out the relative formula mass of the sodium carbonate .XH2O. We know that we had 626 milligrams of it, and we know the number of moles of it. I'm going to come and work down here. So we know that MR is mass over moles. The mass is 0.627 grams. Number of moles is 0.00505. So the MR is 0.627 divided by 0.00505, 124 grams per mole. Okay, how does that help us? Well, we know that the sodium carbonate bit of this, the Na2CO3, 2 times 23 plus carbon plus 3 lots of oxygen, so that's 46 plus 12 plus 48, which is 106 grams per mole for this bit. So how many waters do we have? Well, 124 minus 106 tells us, if I do that in my head, 18. So we've got 18 grams per mole of water. That's one water molecule. If it had been 36, that would have been 2 waters. If it had been 54, that would have been 3 waters. But it tells us that we've only got 1 water molecule for 1 part sodium carbonate. So X must equal 1. Let's have a look at the mark scheme. So the first mark was for the number of moles of sodium hydroxide used in the titration. The second mark was for the number of moles of hydrochloric acid, therefore, that were in the conical flask during the titration, multiplied by 10. In other words, the number of moles of hydrochloric acid in the volumetric flask. So 2 steps there for the second mark. The third mark is for realizing the number of moles of hydrochloric acid that were used up in the beaker in that first reaction. And the fourth mark was for realizing the ratio between that hydrochloric acid and the sodium carbonate. So that second equation we generated, where the hydrochloric acid reacted with the sodium carbonate to generate CO2 and H2O, therefore working out the number of moles of carbonate that reacted. The fifth mark here is for doing a conversion of milligrams to grams, and yes, that might seem rather easy, but that's what the fifth mark was for. The sixth mark here was for working out the mass of water in the formula, and finally the seventh mark is for specifically stating that X equals 1. An alternative method that you could have done was worked out the mass of sodium carbonate, just the Na2CO3 that reacted, which is 0.5353 grams, and therefore the mass of water that there must have been in that initial solid. So you started off with 626 milligrams of the hydrated solid. You know that 535 milligrams were the Na2CO3 bit, so therefore you would have had 92 milligrams, which is the H2O bit. So you could work out the number of moles of water and work out the ratio between them, and you would have worked out the same ratio between the water and the sodium carbonate. So that was an alternative way to do it. Here's a question for you to think about. You can have a go at this yourself, draw it out, try and work backwards from the titration. 1.25 grams of crushed limestone was added to 50 centimetres cubed of 1 molar decimetre cubed hydrochloric acid, which was in excess. Mixture was left until all bubbling stopped and was then made up carefully to 250 centimetres cubed with pure water. 25 centimetre cube sample of this was pipetted into a conical flask. Methyl orange added. Sodium hydroxide was added from a burette. 30 centimetre cubed were needed to reach the end point of the indicator. Calculate the percentage of calcium carbonate in the limestone. You are given the 2 equations for this there. Have a sketch, have a go. Okay, 1.25 grams of limestone. Put in a beaker, 50 centimetres cubed of hydrochloric acid at 1 molar. The final solution was made up to 250 centimetres cubed with water, 25 centimetres cubed taken for titration, and it took 30 centimetres cubed of 0.1 mole of sodium hydroxide to neutralise that. If you haven't already had a go, I strongly suggest you pause the video now and see if you can work backwards from the titration now. Okay, moles of sodium hydroxide, 0.003. Therefore, moles of HCl in the conical flask, 0.003, 1-to-1 ratio. Therefore, moles in the volumetric flask is 10 times that, 0.03. We started on the left in the beaker with 0.05 moles of hydrochloric acid, so therefore the amount used in the first reaction is 0.02 moles. From the ratio, from that equation, we know that it's a 1-to-2 ratio, so 0.01 moles of calcium carbonate reacted. We can work out that the mass of that would have been 1 gram. So we've got 1 gram of calcium carbonate in 1.25 grams of limestone, so the purity is 80%. Notice how a table's not really going to help you with this, because every time there's something slightly different. In that first example, we were asked to work out the number of moles of water. Now we're asked to work out a percentage purity. It's very difficult to learn this sort of thing by rote. You've just got to understand what you're doing. Here's the second question. I'm not going to bother to read it out. See if you can sketch it out. See if you can do it. Zinc in acid, made up to 250 centimetres cubed with water. Titrate it. That's how much sodium hydroxide is needed. If you hadn't managed to sketch that out, now see if you can work backwards from the titration. Okay, moles of sodium hydroxide, 0.0036. We know it's a 2-to-1 ratio now, careful with that, so 0.0018 moles of sulfuric acid in the conical flask. Doubling that, multiplying that by 10, we therefore know that there's 0.018 moles of sulfuric acid in the whole flask. We started with 0.025 moles, so therefore we use 0.007 moles in that first reaction. Ratio is 1-to-1, so we use 0.007 moles of zinc. That would weigh 0.455 grams, so therefore percentage purity 0.455 grams over 0.462 times by 100%, 98.4%. Final thing, this is very similar to the example I did. Okay, so 2.86 grams of sodium carbonate dissolved in a certain amount of water, made up to 250 centimetres cubed. Take it for titration, add some indicator. Here we're adding the hydrochloric acid. See if you can work it out from here. Okay, moles of hydrochloric acid, 0.002. That means the number of moles of sodium carbonate in the flask, because of the 1-to-2 ratio, is half that, 0.001. Which means in the whole flask, there must have been 0.01 moles of sodium carbonate. Because we haven't reacted it, that means in the original block, there must have been that number of moles of sodium carbonate. So in this case, what I've decided to do is work out the mass that would be, 1.06 grams. So what accounts for the rest of the mass? Well, the rest of the mass must be the water. So the mass of water must be 2.86 minus 1.06, which is 1.8 grams. How many moles is that? That's 0.1 gram of water. All right, so we've got 0.1 moles of water, and we've got 0.01 moles of the sodium carbonate bit. So that means we've got 10 times as much water as we have sodium carbonate. So therefore the ratio must be 0.10 H2O. Now these are super hard questions. I do want to stress that. But I do also want to highlight that at A level, there's no such thing as a standard titration question. So you can't learn everything by rote. You need to be confident enough with titrations that if they are part of a longer question, you know how to do the maths. You also need to know where to exit your standard titration calculation to continue with the rest of the question. If you do have any questions about these, please do let me know. For some of you, I hope you really enjoyed them and did work them through. For others of you, you might be a bit horrified. It is definitely towards the harder end, but certainly a student aiming for an A or a B at A-level chemistry should be able to do these with no help. Okay, see you in 2 weeks. Bye.